Across the unfathomable stillness of the cosmos, there is a secret current. It is a motion so vast, so inexorable, that it escapes our everyday perception. We feel the solid ground beneath our feet. We see the sun rise and set. We chart the stately procession of the stars across the night sky. Everything seems rooted in a celestial permanence, a dependable clockwork order. Yet this sensation of stability is a profound illusion. Our planet, our sun, our entire galactic home are all caught in a cosmic drift. We are passengers on a river of space-time, being pulled by an unseen force, a force of such magnitude that it tugs on 100,000 galaxies at once. This is not the gentle, uniform expansion of the universe, pushing everything apart. This is something else, a deviation from the grand cosmic blueprint. It is a specific, directed, and relentless pull toward a single, mysterious point in the southern sky. For decades, we did not even know it existed. We sailed through the void, oblivious to the destination toward which we are hurtling, a destination hidden behind a veil of our own making. This is the story of a gravitational anomaly, a ghost in the cosmic machine, a mystery that, in our attempts to solve it, completely redrew the map of our universe. This is the story of the Great Attractor, and the even greater enigmas that lie beyond. Our tale begins not with a single discovery, but with a dawning, unsettling awareness. In the mid-20th century, cosmology had achieved a kind of elegant simplicity. Edwin Hubble had shown us that the universe was expanding. Galaxies, great islands of stars, were all receding from one another. Like raisins in a rising loaf of bread, the fabric of space-time itself was stretching. This cosmic expansion, the Hubble flow, became the bedrock of modern cosmology. It predicted that, on the largest scales, the movement of galaxies should be uniform. Their velocity away from us should be directly proportional to their distance. And for the most part, the universe seemed to play by these rules. But science thrives on the exceptions, the tiny discrepancies that whisper of a deeper truth. By the 1970s, astronomers had developed increasingly precise methods to measure cosmic distances. They could now begin to untangle a galaxy's motion through space from the motion of space itself. This personal, localized movement is known as peculiar velocity. Imagine a flotilla of boats drifting out from a central point on a perfectly even tide. That tide is the Hubble expansion, but now imagine each boat has its own small motor and a captain with their own agenda. Some boats might be moving slightly faster or slower than the tide. Some might even be veering off to one side, nudged by a local current. That extra, individual motion is the peculiar velocity. When astronomers started measuring these peculiar velocities, they found something astonishing. The boats in our cosmic flotilla were not moving randomly. A significant number of them, including our own Milky Way, all had their motors pointed in roughly the same direction. Our local group of galaxies, the Virgo Supercluster, the Hydra Centaurus Supercluster. Everything within a swath of space, hundreds of millions of light-years across. All of it was streaming at a staggering 600 kilometers per second toward a single area. It was a coordinated, large-scale flow, a cosmic conspiracy of motion. The universe was not a uniform, expanding loaf of bread after all. It was a landscape with gravitational valleys and mountains, and we, along with our countless neighbors, were all sliding downhill into the same colossal basin. The question was, what or who was at the bottom of it? The challenge fell to a group of 7 astronomers in the 1980s. Their collaboration would become so legendary, they earned an enduring nickname, the 7 Samurai. Alan Dressler, Sandra Faber, Donald Lyndon Bell, David Burstein, Roger Davis, Roberto Terlevich, and Gary Wiegner. They embarked on an ambitious, painstaking campaign to map this strange cosmic current. Their method was both brilliant and arduous. They studied a specific type of galaxy, the elliptical galaxy, which is older and more uniform. They discovered a relationship between the brightness of an elliptical galaxy and how fast its stars were moving. This relationship, known as the Faber-Jackson relation, allowed them to calculate a galaxy's intrinsic luminosity. It was like knowing that all 100 watt light bulbs have the same true brightness. By measuring how dim a distant 100 watt bulb appears, you can precisely calculate its distance. The Seven Samurai used elliptical galaxies as their standard light bulbs, their cosmic yardsticks. They could now measure a galaxy's distance with unprecedented accuracy. Then, they measured each galaxy's redshift, the stretching of its light due to its motion away from us. This redshift had two components: the part from the universe's expansion and the part from its peculiar velocity. Since they now knew the precise distance, they could calculate the expected redshift from expansion alone. Anything left over, any extra redshift, or even a blue shift, was the galaxy's own peculiar motion. For 6 years, they pointed their telescopes to the southern skies, gathering data from over 400 galaxies. It was a monumental feat of observational astronomy, a meticulous survey of our cosmic neighborhood. As the data points accumulated, a picture began to emerge from the statistical noise, a picture that was both breathtaking and deeply mysterious. Their map showed a coherent flow, a river of galaxies, and at the heart of that flow, where all the currents converged, was a nexus of immense gravity. They had located the source of the pull. It was a concentration of mass, equivalent to tens of quadrillions of suns. An object so colossal, it was warping the space-time around it for hundreds of millions of light years. They gave this unseen entity a name worthy of its scale and its mystery: the Great Attractor. Pinpointing the location of this cosmic behemoth presented a formidable challenge. The Great Attractor was located in the direction of the constellations Centaurus and Norma. Unfortunately, this placed it directly behind the plane of our own Milky Way galaxy. This swath of the sky, teeming with stars, gas, and thick dust, is known to astronomers as the zone of avoidance. It is our galaxy's own obscuring fog bank, a curtain of material that blocks our view of the deep universe beyond. Trying to observe the Great Attractor with visible light telescopes was like trying to see a distant mountain range through a blizzard. We could feel its influence, the gravitational pull that tugs on our own galaxy. We could see its effects on the galaxies around us, like watching leaves swirl around an invisible drain. But the source itself remained shrouded, a phantom lurking just beyond our sight. This cosmic game of hide-and-seek forced astronomers to become more creative. They had to find ways to peer through the galactic veil. The solution lay in observing the universe in wavelengths of light that are invisible to the human eye. Infrared light, for instance, is better at penetrating dust clouds than visible light. Infrared surveys began to reveal the dim glow of previously hidden galaxies in that direction. Radio waves, with their long wavelengths, could pass through the dust almost entirely unimpeded. Radio telescopes mapped the distribution of hydrogen gas, tracing the faint outlines of galactic structures. But the most powerful tool for piercing the gloom was X-ray astronomy. Galaxy clusters are not just collections of stars, they are filled with enormous clouds of superheated gas at temperatures of millions of degrees. This impossibly hot gas shines brightly not in visible light, but in X-rays. And X-rays, like radio waves, can slice through the Milky Way's dust with ease. When X-ray telescopes were pointed toward the suspected location of the Great Attractor, they saw it. Not a single object, but a vast, sprawling conglomeration of galaxies. At its core lay the Norma cluster, a rich and massive galaxy cluster in its own right. But it was clear that the Norma cluster was just one part of a much larger superstructure. The Great Attractor was not a single, monstrous thing. It was a gravitational focal point, a basin where numerous filaments of the cosmic web converged, a cosmic city center, drawing in matter from the surrounding galactic suburbs. It was a diffuse, sprawling overdensity of dark matter, hot gas, and thousands upon thousands of galaxies. The mystery seemed to be solved. We were being pulled by a colossal collection of cosmic matter hidden behind our own galaxy's glare. Our journey across the cosmos had a destination. But the universe is rarely so simple. As our maps grew more detailed and our understanding more profound, a new complication arose. The solution to the first mystery was about to become the prelude to an even greater one. The discovery of the Great Attractor was a landmark achievement. It revealed the lumpy, uneven texture of the universe and the power of gravity on immense scales. It seemed to provide a complete explanation for our galaxy's peculiar motion. However, a nagging question persisted among cosmologists. The calculated mass of the Great Attractor, vast as it was, didn't seem quite enough. Based on the best estimates from the visible galaxies and the X-ray emitting gas, it accounted for a significant portion of our motion, but not all of it. There was still a residual velocity, a remaining component of our cosmic trajectory that was left unexplained. It was as if we had discovered the powerful river current pulling our boat, but we then realized the entire river itself was flowing downhill. The Great Attractor was just a local waypoint, not the ultimate destination. The entire system, our galaxy, the local group, the Virgo Supercluster, and the Great Attractor itself. This whole enormous volume of space was part of an even grander, more majestic flow. To understand this, we need to redefine what we mean by here in the universe. For decades, we defined our cosmic address by proximity. We lived on Earth, in the solar system, in the Milky Way galaxy, in the local group, which was part of the Virgo Supercluster. This was a nested hierarchy based on physical grouping. But in 2014, a team led by astronomer Brent Tully proposed a revolutionary new way to map the cosmos. Instead of grouping galaxies by how close they are, they grouped them by where they are going. They mapped the gravitational flows, the paths that galaxies take as they fall towards centers of mass. They defined a supercluster not as a simple collection of matter, but as a gravitational basin. Imagine a watershed on Earth. Every drop of rain that falls within that watershed will eventually flow into the same river and end up in the same basin. Tully's team applied this concept to the universe. They mapped the peculiar velocities of tens of thousands of galaxies. They drew the gravitational boundary lines, the cosmic equivalents of continental divides. On one side of the line, a galaxy would fall toward one supercluster. On the other side, it would fall toward another. When they mapped our local region, they made a stunning discovery. The Virgo Supercluster, which we had long considered our home, was just a small province. It was merely an outlying suburb of a much grander structure. Our Milky Way, the Great Attractor, and roughly 100,000 other galaxies all belonged to a single, vast gravitational basin, a supercluster of unimaginable proportions, stretching over 520 million light-years from end to end. They gave this colossal structure a Hawaiian name, befitting its heavenly scale. Laniakea, meaning immeasurable heaven. Our cosmic address had been rewritten. We were residents of the Laniakea Supercluster, and the Great Attractor, the object we thought was the prime mover, was revealed to be just the gravitational heart of our local basin. It is the point towards which everything within Laniakea is slowly, inexorably falling. But the new map also confirmed the lingering doubt. Laniakea, this entire cosmic continent of galaxies, was itself in motion. The whole structure was being tugged by something even more massive, something far outside its own boundaries. The search for the true source of our cosmic velocity was on again. The Great Attractor was no longer the final answer. It was just a clue, pointing the way toward an even more formidable power, lurking deeper in the cosmos. To find the source of Laniakea's motion, astronomers had to cast their nets wider than ever before. They needed to look beyond the Great Attractor, beyond the zone of avoidance. They peered hundreds of millions of light-years deeper into the cosmic ocean, and there, they found it. A structure of such staggering immensity it almost defied comprehension. It had actually been first noted decades earlier, in the 1930s, by the legendary astronomer Harlow Shapley. While surveying the distribution of galaxies in the southern sky, Shapley noticed a remarkable cloud of them, a region of space where the density of galaxies was exceptionally high. At the time, the scale and significance of this discovery were not fully appreciated. It was just one more curious feature in a universe full of wonders. But with the new understanding of cosmic flows, Shapley's cloud was re-examined, and it was revealed to be the true titan of our local universe. It is called the Shapley Supercluster. If Laniakea is a vast continent, then the Shapley Supercluster is an entire world. Located about 650 million light-years from us, it is the largest and densest concentration of galaxies in our cosmic vicinity. It contains over 8,000 galaxies, with a total mass more than 10 million billion times that of our Sun. It is a cosmic metropolis so crowded, so gravitationally dominant, that its influence is felt across the universe. This is the object that is pulling on our entire Laniakea supercluster. The mystery was now laid bare in all its magnificent complexity. Our galaxy, the Milky Way, is falling toward the center of the local group. The local group is falling toward the Virgo cluster. The Virgo cluster, and everything around it, is falling toward the Great Attractor. And the entire Laniakea supercluster, containing all of these structures, is being pulled across the universe. Its destination, the incomprehensibly massive Shapley supercluster. It's a nested, hierarchical fall, a cascade of gravitational attraction on a mind-boggling scale. We are not just on a river, we are on a tributary, which flows into a larger river. That river system forms a continental watershed, Laniakea, and that entire watershed is draining into a vast cosmic ocean called Shapley. This grand cosmic flow is a direct and beautiful confirmation of our modern understanding of the universe. It is a visible manifestation of the underlying structure that governs everything. This structure is known as the cosmic web. When we zoom out to the largest possible scales, the universe does not look like a random scattering of galaxies. Instead, it resembles a gigantic, three-dimensional spider's web. This cosmic web is composed of immense, thread-like filaments of dark matter. Galaxies and galaxy clusters are strung along these filaments like pearls on a necklace. These filaments stretch for hundreds of millions of light-years, connecting and weaving through the cosmos. Where the filaments intersect, they form dense, massive nodes. These nodes are the superclusters, like Shapley and the heart of Laniakea. Surrounding this intricate network are vast, empty regions of nearly nothing. These are the great cosmic voids, profound emptinesses that can be a billion light-years across. The cosmic web is the skeleton of the universe, and gravity is its architect. In the very early universe, matter was almost perfectly uniform, but there were minuscule quantum fluctuations in density, tiny spots that were infinitesimally more massive than others. Gravity, ever patient and persistent, began to work on these tiny seeds. Over billions of years, it amplified them. The slightly denser regions pulled in more matter, becoming even denser. Matter drained away from the less dense regions, creating the voids. The cosmic flows we observe today are simply this process of structure formation in action. Galaxies are streaming along the filaments of the cosmic web. They are flowing away from the voids and toward the great nodes. The Great Attractor is a major junction in our local part of the web. The Shapley Supercluster is an even more significant continental hub. Our journey is not a random drift, but a ride along the superhighways of the cosmos. We are following the gravitational contours laid down by dark matter over 13.8 billion years. It is a process of cosmic assembly, gravity slowly building the great cities of the universe. But this grand construction project has a powerful and mysterious adversary. There is another force at play in the cosmos, one that is working against gravity, a force that is trying to tear the cosmic web apart. This force is called dark energy. While gravity pulls matter together, dark energy pushes space-time apart. It is a repulsive force, an intrinsic property of the vacuum of space itself, and critically, it is winning the cosmic tug-of-war. In 1998, astronomers discovered that the expansion of the universe is not slowing down as expected. It is accelerating. The space between galaxy clusters is stretching at an ever-increasing rate. This introduces a profound and poignant twist into the story of our cosmic journey. We are being pulled toward the Great Attractor, which is being pulled toward the Shapley Supercluster. Gravity is commanding us to fall towards these immense structures, but the dark energy-fueled expansion of space is working against that command. The very fabric of the universe between us and our destination is expanding, and it is expanding faster and faster every moment. So, will we ever arrive? Will the Milky Way one day merge with the galaxies of the Norma cluster at the heart of the Great Attractor? Will our entire Laniakea Supercluster eventually collapse into the Shapley Supercluster? The answer, according to our best current understanding, is almost certainly no. The distances are simply too vast, and the force of dark energy too powerful. The space between us and the Great Attractor is growing faster than we can traverse it. We are like a runner on a cosmic treadmill that is constantly speeding up. We are running toward a finish line that is receding from us faster than we can run. Our local group of galaxies, bound by gravity, will eventually merge into one giant galaxy. But the great structures beyond, the destinations that have guided our motion for eons, are slipping away. They are being pushed over a cosmic horizon beyond our reach forever. In the far distant future, as cosmic expansion continues to accelerate, the universe will become a much lonelier place. Distant superclusters like Shapley will recede so fast their light will no longer be able to reach us. They will vanish from our sky as if they never existed. Future astronomers in our galaxy will look out into a universe that appears almost empty. The great cosmic web will have been stretched to the breaking point. The grand evidence of cosmic flows and large-scale structure will be gone, erased by dark energy. We live in a privileged epoch, a brief window of cosmic time where we can still see the grand narrative. We can still map the rivers and watersheds of the cosmos. We can witness the magnificent battle between gravity's pull and dark energy's push. The journey to understand the Great Attractor has been a profound lesson in cosmic humility. It has reshaped our place in the universe, time and time again. First, we learned we were not stationary, but part of a colossal galactic flow. Then, we identified the source of that flow, a hidden mass behind our own galaxy. Then we discovered that this source was itself just a local landmark in a far larger structure, Laniakea. And finally, we found that our entire celestial continent is on a pilgrimage toward an even greater mass, the Shapley Supercluster, a destination we are fated to pursue but never to reach. Each step of this journey has revealed a universe more complex, more structured, and more magnificent than we had ever imagined. It shows us that everything is connected, from the smallest quantum fluctuations in the early universe to the grandest superclusters of today. Our Milky Way is not an isolated island, but a participant in a dynamic, evolving cosmic ecosystem. The mystery of our motion has led us to the very architecture of creation. We now understand that we are living inside the process of cosmic structure formation. We are witnessing the slow, majestic assembly of the universe, even as another force works to unravel it. The silent, invisible current that pulls on our galaxy is the echo of the Big Bang itself. It is the enduring legacy of gravity, written across billions of light years. And though our final destination may forever lie beyond our grasp, the journey itself is the revelation. It is a journey of discovery that continually expands our horizons. And it reminds us that in this vast, mysterious cosmos, there are always greater attractors and deeper enigmas waiting to be found. The river flows on, and we flow with it, forever falling through immeasurable heaven. How does a galaxy bleed? The question feels wrong, a violation of scale and substance. Galaxies are not living things. They are incomprehensibly vast collections of stone and fire, of stellar furnaces and frozen worlds, bound by the silent, indifferent arithmetic of gravity. They have no veins, no heart, no circulatory system to wound. And yet when you peer into the deepest chasms of the cosmos, into the crowded, chaotic suburbs of the universe, you can see it happening. You can witness a hemorrhage on a scale that defies all biology, a silent, graceful, and utterly catastrophic bleeding of lifeblood into the cold, unforgiving void. What you're looking at is not a medical anomaly. It is a profound cosmic mystery, a celestial crime scene stretching across millions of light years. Astronomers have given these beautiful tragic spectacles a name one borrowed from the silent drifters of our own oceans. They call them jellyfish galaxies. And once you see one, you understand why. Suspended in the black, the main body of the galaxy glows a familiar spiral of gold and sapphire, a wheel of 100 billion suns still intact, still brilliant. But streaming away from it, pulled and tormented by some unseen force, are its ghostly appendages. Vast, ethereal tentacles of turquoise and magenta, light some trailing for distances greater than the Milky Way itself. They are delicate, wispy, and hauntingly beautiful, like the ink of a squid dispersed in water, or the silken train of a gown caught in a phantom wind. These are not streams of stars. They are something far more fundamental. They are the galaxy's primordial inheritance, its future, its very soul. This is the raw material of creation itself, enormous galaxy-spanning clouds of cool hydrogen and helium gas. This is the reservoir from which new stars are born. Within these clouds, gravity is meant to patiently gather matter-crushing pockets of gas over millions of years until they collapse and ignite in glorious thermonuclear fusion. This gas is the celestial nursery, the stellar womb. It is the promise of generations of suns yet to come, of planets that might one day form in their gentle light of the potential for life itself, and it is all being violently torn away. We are not witnessing a gentle leak or a slow evaporation. We are watching a galaxy being flayed alive. The force required to inflict such a wound is difficult to comprehend, a power capable of overcoming the colossal gravity of an entire island universe, stripping it bare of the very substance that defines its vitality. As this lifeblood streams away into the intergalactic darkness, the galaxy's fate is sealed. Its star formation will slow sputter and eventually cease entirely. The brilliant blue light of its young, massive stars will flicker out, never to be replaced. Over billions of years, it will transform from a vibrant living system into a ghostly relic, a mausoleum of aging red stars. It will become what astronomers morbidly call red and dead, a silent, quiescent monument to a life it once could have lived. This process of slow, inexorable starvation is one of the great and terrible engines of cosmic evolution. It is a key part of the answer to a fundamental question: why are galaxies so different? Why are some like our own Milky Way still blazing with the fire of new creation, while others are little more than cosmic fossils? The answer, it seems, is written in the fading light of these magnificent dying creatures. Their wounds tell a story not just of their own demise, but of the environment they inhabit, a place far more violent and complex than the serene emptiness we might imagine. To understand what is happening to them, you have to change your perspective. You must zoom out far beyond the lone galaxy and see it not as an island, but as a traveller, an immigrant arriving in a new and hostile land. These jellyfish are almost exclusively found in one type of location, the Great Galactic Clusters. These are the metropolises of the universe, the most massive gravitationally bound structures in existence. Imagine a celestial city, not of buildings, but of entire galaxies, hundreds, even thousands of them, all swarming around a common centre of gravity like moths to a flame. From a distance, these clusters are sites of breathtaking beauty, glittering collections of cosmic jewels, but up close, they are cosmic cauldrons. The space between the galaxies here is not empty. It is filled with something unseen, something unexpected. It is an immense invisible ocean of superheated plasma, a tenuous gas heated to millions of degrees hotter than the core of our own sun. This is the intracluster medium, the ICM. It is the gaseous ghost of galaxies long past the accumulated exhaust of billions of years of cosmic history of supernovae and stellar winds from every galaxy in the collective. Though it is incredibly diffuse, far less dense than any vacuum we could create on Earth, its sheer scale makes it a formidable obstacle. It is a trap, a gravitational prison from which there is little escape. Now imagine our unsuspecting spiral galaxy having travelled for billions of years through the relative peace of the cosmic voids, finally feeling the inexorable pull of one of these immense clusters. It accelerates, falling faster and faster into the cluster's deep, gravitational, well-reaching speeds of thousands of kilometres every single second, millions of miles per hour. And then it hits the wall. Not solid wall, but the invisible superheated fog of the ICM. The collision is an event of unimaginable scale and violence, yet it happens in near total silence. The stars and dark matter, being dense and gravitationally powerful, plough through this medium relatively unscathed. But the galaxy's delicate diffuse clouds of cold gas, its precious fuel for star formation, are another matter entirely. They feel the impact as a cataclysmic headwind, a cosmic hurricane of staggering force. This is a process called ram pressure stripping. It is the universe's own brand of hydrodynamics playing out on a stage 1,000,000 trillion times larger than any ocean on Earth. The relentless pressure of the intracluster medium acts like a celestial blowtorch scouring the galaxy, pushing and pulling on its gas reserves. The gas clouds, once safely nestled within the galaxy's gravitational embrace, are ripped from their moorings. They are peeled back layer by layer, starting from the galaxy's outer edges and driving relentlessly toward its core. What we see as the beautiful, serene tentacles of the jellyfish are in reality the visible scars of this unimaginably violent encounter. Each tendril is a testament to the sheer power of this invisible medium, a plume of stolen potential cast adrift in the cluster's fiery halo. We are watching the moment of impact frozen in time by the immense distances light must travel to reach our telescopes. We are detectives arriving at a crime scene that is still unfolding an assault that has been in progress for hundreds of millions of years. The sheer variety in their appearance is a map of their suffering. Some galaxies show only the faintest hints of disturbance, the first signs of a wisp of gas being tugged away at the edges, like a thread pulled from a tapestry. These are the newcomers' galaxies just beginning their perilous journey into the cluster's heart. Others exhibit more dramatic one-sided tails, clear evidence of the direction of the cosmic wind they are fighting against. They look like cosmic comets, their stellar bodies forming the nucleus while their gaseous souls trail behind them. And then there are the most extreme cases, the true jellyfish, where the stripping process is so intense and has been going on for so long that the galaxy is draped in a spectacular sprawling network of filaments. These are the veterans of the cluster environment galaxies that have survived their first pass through the dense core and are now paying the ultimate price. The sight is a profound paradox. We are witnessing the death of a galaxy's future, the slow extinguishing of its creative fire. Yet in that very process of destruction, new life is being sparked in the most unexpected of places. Within those trailing tormented tentacles of gas, something remarkable is happening. The same ram pressure that strips the gas can also compress it. Pockets within the tails are being squeezed, triggering frantic, unexpected bursts of star formation far outside the traditional confines of the galactic disk. Look closely into those turquoise filaments, and you will see them brilliant blue knots of light like tiny incandescent pearls strung along the ghostly limbs. These are newborn star clusters, orphan suns ignited in the chaotic wake of their parent galaxy. They are stellar children born in exile. They will never know the warmth and gravitational stability of the galaxy that gave them life. They are destined to wander the lonely, perilous space between galaxies, a scattered diaspora of stars created by a moment of cosmic trauma. These fireballs are a stunning confirmation of the theory, a beautiful and poignant consequence of the violence. A galaxy bleeds, and in its very wounds, for a fleeting cosmic moment, new stars are born. It is a process of simultaneous death and birth, of destruction and frantic, defiant creation, a cycle of cosmic life playing out on the grandest possible scale. This discovery has transformed our understanding, turning these jellyfish from mere curiosities into vital cosmic laboratories. They provide a unique real-time snapshot of gas physics under the most extreme conditions imaginable. By studying the length and structure of their tentacles, we can measure the density of the invisible intraclunar medium. The tails become cosmic windsocks, telling us about the direction and ferocity of the currents swirling within the cluster. By analysing the chemistry of the stripped gas, we can probe the history of the galaxy itself, sampling material from its outer regions that would otherwise be impossible to observe in such detail. Each jellyfish galaxy is a unique experiment, a story of an encounter between a single galaxy and its colossal environment. And by studying hundreds of them, we begin to piece together the rules of life and death in these cosmic cities. We learn how galaxies are transformed, how their evolution is shaped not just by their internal processes, but by the relentless shaping hand of their surroundings. This story, however, is not merely about distant alien worlds. It is a preview of a possible, perhaps even probable future for our own home. The Milky Way is not an island unto itself. We are part of a small, gravitationally bound collection of galaxies called the Local Group, and our entire Local Group is a traveller. We're falling even now at over 1 million miles per hour toward the nearest great metropolis, the Virgo cluster. In a few billion years, our descendants, should they exist, may witness our own galaxy beginning its final fiery plunge into that vast incandescent fog. They may watch as the Milky Way, our home, our celestial cradle, begins to feel the first gentle caress of that cosmic wind, a wind that will grow into an unstoppable gale. Will our galaxy one day become a jellyfish? Will its own vibrant star-forming gas clouds be torn away, strung out across the Virgo cluster in magnificent tragic tendrils? Will our distant future be one of slow starvation of our brilliant spiral fading to a ghostly quiescent red? The jellyfish we see in the deep cosmos today are not just objects of study. They are messengers from a distant future. They are a memento mori on a galactic scale, a reminder that even the grandest structures in the universe are not eternal. They are subject to the forces of their environment, shaped and ultimately consumed by the very universe that created them. And so we are compelled to look closer to decode the secrets written in their trailing streams of light. The challenge is immense. This gas is astonishingly faint, its glow easily lost in the overwhelming brilliance of the background stars and galaxies. It requires our most powerful telescopes, our most sensitive instruments, and thousands of hours of painstaking observation to trace these ghostly appendages and unravel the physics at play. We must build vast computer simulations, creating virtual universes and supercomputers to replicate this process, to test our theories against the silent, beautiful evidence provided by the cosmos itself. Every new image, every data point brings us a little closer to understanding this spectacular process of galactic transformation. And with that understanding comes a deeper appreciation for the complexity and fragility of the cosmos. The universe is not a static, serene stage. It is a dynamic, evolving ecosystem filled with predators and prey, with zones of safety and regions of extreme peril. The story of the jellyfish galaxies is a crucial chapter in the grand narrative of how this cosmic ecosystem came to be. It is the story of how the great red and dead elliptical galaxies that dominate the centers of clusters were formed. It is the story of how the very structure of the universe is assembled, one stripped and strangled galaxy at a time. As we journey forward, we must ask the next set of questions. Just how much of a galaxy's gas is lost, and how quickly can a galaxy ever survive the encounter, perhaps holding on to a small reservoir of gas deep within its core? What happens to the billions of orphaned stars born in the tentacles? Do they form their own tiny ghost galaxies, or do they simply disperse into the intracluster darkness, becoming a faint unseen shimmer in the spaces between their larger cousins? And what can these bleeding giants tell us about the even more mysterious substance that holds them together, dark matter? Does its invisible scaffolding also get distorted by this violent passage? The mystery of the jellyfish galaxies is no longer just about why they are bleeding. It is now about what their wounds can teach us. They are beacons illuminating the invisible forces that govern the cosmos, revealing the turbulent weather of intergalactic space. They are both a warning and a spectacle, a tragedy and a revelation. They force us to see galaxies not as majestic, isolated islands, but as vulnerable entities intimately connected to and profoundly shaped by the vast dark ocean in which they swim. Their story is just beginning to be told, and it is a story that will reshape our understanding of what it means to be a galaxy in a vast and violent universe. What if a galaxy could bleed? Not in a metaphorical sense, but a literal one, hemorrhaging its lifeblood, the very gas needed to form new stars into the cold, dark void. For most of human history, we viewed galaxies as eternal monuments, serene islands of light floating in a placid cosmic ocean, each one a self-contained universe bound by its own immense gravity. They were the constants, the fixed points of celestial architecture against which the fleeting lives of stars and planets played out. We saw them as majestic, isolated, and above all permanent. But this grand, comforting vision, like so many of our first cosmic intuitions, was profoundly, beautifully wrong. The universe we were about to discover is not a quiet gallery of static masterpieces. It is a battlefield. And on that battlefield, galaxies are not just participants. They are victims sculpted and scarred by forces we were only just beginning to imagine. Our journey into this violent reality doesn't begin with a single dramatic explosion, but with a quiet accumulation of anomalies, a slow-growing catalogue of cosmic oddities that refuse to fit our neat models. By the mid-20th century, as our telescopes grew more powerful, astronomers were peering deeper into the cosmic tapestry, and what they found were not just elegant spirals and placid ellipticals. They found the strange ones. Galaxies that looked as if they had been in a fight, their spiral arms distorted and flung wide, their cores offset, their shapes twisted into question marks and exclamation points against the black. The astronomer Halton Arp, a meticulous and sometimes controversial observer, dedicated himself to this pursuit, compiling his groundbreaking Atlas of Peculiar Galaxies. It was a celestial rogues gallery, a collection of cosmic misfits and nonconformists. There were galaxies that seemed to be connected by impossibly thin bridges of stars, others that looked like they were exploding, and still more that possessed strange ethereal jets erupting from their centres. At first, these were treated as curiosities, exceptions that proved the rule of galactic decorum. Perhaps they were the result of rare cataclysmic collisions, cosmic train wrecks that were spectacular but statistically insignificant in the grand scheme of things. Yet a subtle and persistent pattern began to emerge from the noise, a clue hiding in plain sight. When astronomers mapped the locations of these battered and bruised galaxies, they found they weren't randomly scattered across the heavens. They clustered. They congregated in specific regions of space neighborhoods where the cosmic real estate was far more crowded. These were the great galaxy clusters, the sprawling, glittering metropolises of the universe, and it became inescapably clear that if you wanted to find a galaxy that was suffering, you had to go to the big city. Imagine a city not of millions, but of thousands of galaxies, each one a swirling empire of billions or even trillions of stars. This is a galaxy cluster. Our own Milky Way is a resident of a quiet, sparsely populated suburb we call the local group, with only one other large neighbour, Andromeda, and a smattering of smaller dwarf galaxies. But a true cluster like the Virgo cluster or the colossal Coma cluster is an entirely different beast. It is a roaring, chaotic gravitational maelstrom. Here, thousands of galaxies are crammed into a volume of space that would be considered practically empty out in the cosmic hinterlands. They aren't sitting still. They're careening through the cluster's heart at astonishing speeds, moving at millions of kilometers per hour, their orbits dictated by the crushing collective gravity of the entire system. This is a world of constant encounters of near misses and high-speed flybys, a place where a galaxy's personal space is perpetually invaded. The sheer density of these cosmic cities was the first obvious suspect in the mystery of the peculiar galaxies. The reigning hypothesis, and a powerful one, was rooted in the force we understand best, gravity. We call it tidal interaction, or sometimes more evocatively galactic harassment. Think of it as a gravitational tug-of-war on a cosmic scale. When one galaxy passes close to another, its gravity doesn't pull on its neighbour uniformly. The side of the galaxy that is closer gets pulled more strongly than the side that is farther away. This differential pull, this stretching force, is what creates tides on Earth. But when applied to entire galaxies over millions of years, the effects are far more dramatic. It's a silent, relentless assault. A passing neighbour can act like a ghostly hand reaching across space to warp a perfect spiral disk, pulling out long, trailing streamers of stars and gas known as tidal tails. For a time, this seemed to be the perfect explanation. It accounted for the bridges of light connecting some galaxies and the long, elegant tails trailing others. It made sense that in the packed urban environment of a cluster, where galaxies are constantly brushing past one another, such gravitational sculpting would be commonplace. The evidence was compelling. We could run computer simulations that showed how two interacting spiral galaxies could, after a complex gravitational dance, morph into the very same bizarre shapes catalogued by ARP. The case seemed to be closing. The culprit behind the cosmic vandalism was gravity, the familiar force that governs everything from falling apples to the orbits of planets. The crime scene was the cluster, and the motive was simply proximity. But the universe is rarely so simple. A deeper, more mysterious clue was waiting to be uncovered, lurking not in the bright shining galaxies themselves, but in the seemingly empty space between them. The great illusion of a galaxy cluster is that it is composed of islands of matter, the galaxies floating in a perfect vacuum. This could not be further from the truth. The space between the galaxies in a cluster is not empty, it is filled. It is permeated by something vast, ancient, and almost entirely invisible, the intracluster medium. This isn't cold, placid gas. It is an immense ethereal ocean of plasma, superheated fog of protons and electrons, heated to unimaginable temperatures often reaching tens or even hundreds of millions of degrees Celsius. That is far, far hotter than the core of our own sun. It is a ghostly furnace that spans millions of light years, containing as much and sometimes more mass than all the stars in all the galaxies of the cluster combined. How could something so incredibly hot be invisible to our eyes? The answer lies in its density. This plasma is extraordinarily tenuous, more diffuse than any vacuum we can create in a laboratory on Earth. There are only a few hundred particles per cubic meter, so while each individual particle is screaming with thermal energy, there are so few of them that the overall light they emit is incredibly faint, radiating primarily in the X-ray portion of the spectrum, completely invisible to optical telescopes. For decades, this colossal reservoir of superheated matter went completely undetected. It was the dark horse, the hidden variable in the cosmic equation of the city. When our X-ray telescopes finally opened their eyes to the sky, in the latter half of the 20th century, they revealed this staggering truth. The cosmic cities were not empty spaces with glittering galaxies inside them. The galaxies were more like celestial fish swimming through a scalding invisible sea that filled the entire volume of the cluster. This discovery changed everything. Suddenly, gravity was no longer the only suspect. There was a new force to consider, a new actor on the cosmic stage. If a galaxy is not moving through an empty vacuum but is instead plunging at 1,000 kilometers per second through a tangible, albeit incredibly thin medium, then it must experience something akin to a wind, a cosmic headwind. Imagine driving your car at high speed into a rainstorm. The faster you go, the more forcefully the rain strikes your windshield. Now scale that up. A galaxy with its vast, delicate disk of stars, and more importantly its loosely bound halo of cool gas, is plummeting through this ultra-hot plasma ocean. As it moves, the pressure exerted by this intergalactic medium on the galaxy's own gas could be immense. It would act like a celestial blowtorch, a relentless gale-force wind pushing against the galaxy's direction of travel. This nascent idea was revolutionary. Could this ethereal wind, this pressure from an almost imperceptible medium, be strong enough to fundamentally alter the structure of a billion-star system? Could it be the force responsible for stripping away a galaxy's precious gas, the very fuel it needs for future generations of stars? It was a difficult concept to accept. Gravity is a brute force easy to conceptualize. Its effects are dramatic and obvious. This new mechanism, which would come to be known as ram pressure stripping, was something far more subtle. It was a persistent wearing force, an act of cosmic erosion, rather than a violent collision. It suggested that galaxies weren't just being pulled apart by their neighbours, they were being actively scoured and sandblasted by the very environment they inhabited. The debate ignited. On one side were the proponents of gravity, pointing to the clear evidence of tidal tails and distorted stellar disks, phenomena that ram pressure could not easily explain. Tidal forces act on everything stars, gas, dark matter, pulling and stretching the entire galactic structure. On the other side were the champions of this new cosmic wind, who argued that gravity couldn't be the whole story. They began to look for a specific kind of evidence, a unique signature that could only be left by ram pressure. While tidal interactions tend to be messy and chaotic, often affecting both galaxies in an encounter, and creating two-sided tails, the theoretical effects of ram pressure were different. It would be a one-way street, a relentless directional force always pushing from the front like the wind on a speeding runner. It wouldn't significantly affect the tightly bound stars, which are like dense pebbles in the wind, but it would have a devastating effect on the diffuse expansive clouds of interstellar gas, the galaxy's lifeblood. It would push this gas backward, peeling it away from the galactic disk and leaving it to trail behind like a plume of smoke in a hurricane. astronomers went back to their plates, back to their data, looking at the peculiar galaxies of the clusters with new eyes. They weren't just looking for distorted shapes anymore. They were searching for a specific pattern of damage for evidence of this cosmic bleeding. They started finding them. Galaxies deep within the fiery heart of the great clusters that looked strangely lopsided. They were still beautiful spirals, but they possessed an unnerving asymmetry. On one side, the edge of their stellar disk was sharp and well-defined, with vibrant blue knots of recent star formation, a sign of gas being compressed and ignited by the incoming pressure. But on the other side, the trailing edge, there was nothing, a deficit of gas. And trailing behind the entire galaxy, visible now with more sensitive radio and X-ray telescopes, were vast, unmistakable plumes of gas stretching for hundreds of thousands of light-years into the intra-cluster medium. These were not the elegant star-filled tidal tails created by gravitational waltzes. These were something else entirely. These were tails made almost purely of gas-stripped raw from the parent galaxy. They were wounds. They were evidence of an ongoing assault, a galaxy being flayed alive by the invisible ocean it was forced to swim through. While gravity was undoubtedly a major sculptor of galaxies, particularly in creating dramatic stellar bridges, and tails, these specific gas-rich, one-sided plumes, pointed an incriminating finger directly at the hot, dense medium of the cluster. The cosmic city wasn't just a place of gravitational harassment. It was a hostile environment with an atmosphere that could kill. And as we trained our most powerful instruments on these bleeding galaxies, we saw that their trailing tendrils of gas were not just random smears. They were intricate, complex, and hauntingly beautiful, filled with shock fronts, turbulence, and even new orphaned stars being born in the stolen gas. They resembled the delicate trailing tentacles of a familiar creature from our own terrestrial oceans, a name that would soon become synonymous with this extraordinary process of galactic transformation, leading us to the heart of our story. Undefined. But curiosity in science is a powerful engine of creation. It builds new eyes, new ears, new senses with which to perceive the universe. And as the 20th century bled into the 21st, our senses sharpened. The era of peering through eyepieces, of capturing faint smudges on glass photographic plates, was giving way to a new age of discovery. It was an age of silicon and superconductors, of immense mirrors, polished to tolerances finer than a wavelength of light lofted into the black vacuum above our turbulent atmosphere. We were no longer just looking at the cosmos, we were beginning to interrogate it. The first hints that these jellyfish were more than just galactic oddities came not from what we could see, but from what we couldn't. Radio astronomy, the unsung hero of modern cosmology, opened a window onto a universe that shines with no visible light. Giant dishes linked together across entire continents formed a single, planet-sized ear, listening for the faintest whispers from the coldest, darkest corners of intergalactic space. They were tuned to a specific frequency, a subtle hum at 21 centimeters, the spectral signature of cold, neutral hydrogen gas. This is the raw fuel of creation, the elemental building block from which all stars and eventually all planets and people are forged. When these new radio eyes were turned towards the known jellyfish galaxies, the image that slowly resolved on astronomers' screens was staggering. The delicate ghostly tails seen in visible light were revealed to be just the luminous froth on an invisible continent-sized ocean of gas. Where optical telescopes saw a faint wisp, radio telescopes mapped a colossal river. These were not mere trickles of lost material. They were tidal waves of hydrogen unimaginably vast, stretching for hundreds of thousands, sometimes millions of light years. Imagine a structure so vast that light itself, the fastest thing in existence, would take longer to cross it than our species has spent evolving from our earliest hominid ancestors. These were not tails. They were umbilical cords of doom, siphoning the very lifeblood from their parent galaxies. The sheer quantity of gas was breathtaking, often equaling the entire remaining gas reservoir within the galaxy's disk itself. This wasn't a minor injury, it was a catastrophic hemorrhage. For a spiral galaxy, its cold gas is its future. It is the promise of new generations of stars, new solar systems, the potential for life. To lose this gas is to be sentenced to a slow, inexorable decline, into a red and dead relic, a stellar graveyard populated only by aging, dying stars. The evidence was undeniable. We were witnessing the process of galactic strangulation. In real time, a slow-motion murder played out on a scale of hundreds of millions of years. The picture became even more detailed, more violent when we brought our most powerful optical instruments to bear. Telescopes like the Hubble Space Telescope and the ground-based Very Large Telescope in Chile's Atacama Desert provided a resolution so sharp it was like moving from a distant blurry photograph to standing right in front of the subject. We could now see the fine structure within the chaotic tails, the tangled filaments, the shock fronts, the turbulent eddies. The clean, almost artistic sweep of the early images was replaced by the raw, visceral complexity of a cosmic cataclysm. It looked less like a gentle bleeding, and more like a high-speed collision, as if the galaxy had been sandblasted by an invisible cosmic wind. Every new piece of data pointed towards a process of immense power, a force capable of overcoming the colossal gravity of an entire galaxy and peeling it apart layer by layer, atom by atom. The simple early theories began to crumble under the weight of this new evidence. One idea was that we were seeing the result of gravitational interactions, a cosmic tug-of-war between neighbouring galaxies. This process, called tidal stripping, is common throughout the universe. It sculpts beautiful stellar streams and bridges between colliding galaxies. But the jellyfish tails didn't quite fit. Tidal interactions tend to pull on stars and gas alike, creating broad, gentle arcs of material. What we were seeing here was different. The stars within the jellyfish disk seemed largely undisturbed, their majestic spiral patterns still intact, while only the gas was being violently torn away. It was as if a ghostly hand had reached into the galaxy, ignoring the billions of suns and seized only the diffuse interstellar medium. This was a selective violence, a precise and devastating attack on the galaxy's most vital and vulnerable component. The mystery deepened. We had established the crime scene, we had identified the victim's wounds, but the weapon, the very nature of the assault, remained elusive. We could map the stolen material, measure its mass trace, its tortured path through the intergalactic void. We saw the past in the galaxy's still shining disk, and we saw the bleak future in the stolen gas dissipating into nothingness. The narrative seemed complete, a story of loss, of decay, of a vibrant spiral being stripped bare and left for dead. This was a compelling, if tragic, story, and it was almost completely wrong. Because as we stared deeper into those long, tortured tendrils of gas, something utterly impossible came into view. Something that shouldn't be there. Something that defied all logic. Buried within the maelstrom, shining like brilliant blue diamonds sewn onto a thread of dark silk, were knots of intense, vibrant light. Spectroscopy, the science of breaking light into its constituent colours, provided the definitive, shocking answer. This was not the old reflected light of the parent galaxy. This was the fierce blue-white glare of O-type and B-type stars. These are the titans of the stellar world, massive, brilliant, and incredibly short-lived. They are cosmic blowtorches burning through their nuclear fuel at a furious rate, and they can only be born in the here and now. You cannot find an old O-type star for the same reason you cannot find a week-old stick of dynamite that has been lit. Their presence is an unambiguous signpost, a cosmic flare that screams stars are being born here. Right now. Let the profound absurdity of that discovery sink in. We believed these tales were the galaxy's final dying breaths, a tenuous mist of gas violently ripped from its gravitational anchor and doomed to disperse into the cold, empty void between galaxies. Star formation, as we understood it, is a delicate and demanding process. It requires vast clouds of gas hundreds of light years across to be cold, dense, and relatively quiescent. The gas must be able to cool down, to shed its energy, allowing gravity to gain the upper hand, and slowly, patiently pull the material together into collapsing cores that will ignite as stars. It is a process that happens in the sheltered, protected nurseries, deep within the spiral arms of a galaxy, shielded from harsh radiation and disruptive forces. The environment within a jellyfish tail is the exact opposite of this. It is a chaotic high-velocity war zone. The gas is being stretched, sheared, and heated by the very process that is stripping it away. It is thin, diffuse, and turbulent. By all rights, this gas should be utterly sterile, incapable of collapsing into anything at all. Expecting stars to form in these tails was like expecting a delicate orchid to bloom in the heart of a Category 5 hurricane. And yet, there they were, dozens, sometimes hundreds of these brilliant blue stellar nurseries glittering defiantly in the galactic wreckage. This discovery didn't just add a new chapter to the story, it tore up the entire book. The stripping process, which we had cast as the villain, the agent of galactic death, was somehow also a catalyst for creation. The same force that was killing the galaxy in one place was triggering impossible bursts of new life in another. It was a paradox of cosmic proportions. The victim was bleeding, yes, but its very blood was crystallizing into new life as it spilled out into the void. These were orphan stars born into exile, untethered from the gravitational embrace of their parent galaxy. They would never orbit a galactic center. They would spend their entire lives wandering the lonely darkness of intergalactic space, their only home, a thinning transient stream of gas. What did this mean for the universe? Were the vast, dark spaces between galaxies not as empty as we thought? Were they being seeded with these rogue star systems, forming their own tiny, ghostly dwarf galaxies from the stolen remains of their larger cousins? Could a galaxy die only to give birth to 100 smaller children in its final moments? The questions multiplied with every new observation. The mystery of the jellyfish galaxies had transformed. It was no longer simply about what was happening to them. The focus now shifted to the more fundamental and far more difficult question. How? How could a single process be both destructive and creative? What mysterious force operating unseen within the vast clusters of galaxies possessed this dual nature? A force powerful enough to rip trillions of tons of gas per second from a spiral galaxy, yet somehow in the very same violent act gentle enough to compress pockets of that gas to the point of stellar ignition. It had to be a force that acted on gas but not on stars. It had to be related to the galaxy's rapid motion and its location within the dense environment of a galaxy cluster. The evidence was laid out a complex tapestry of clues: the immense scale of the stripped gas, the undisturbed stellar disks, and the impossible star formation in the tails. All these threads of evidence pointed towards one culprit, one elegant and powerful explanation that could resolve the paradox. A force that is all around us, yet one we never feel. An invisible headwind blowing not of air but of superheated plasma. The time had come to finally name the killer, and so the most obvious suspects have been dismissed. The magnificent bleeding streamers of gas we see trailing from these galaxies are not the result of some violent gravitational collision, some cosmic fender bender between galactic titans. They are not the phantom limbs of a past merger, nor are they explosive jets powered by a central supermassive black hole. The evidence simply does not fit. Each of these powerful phenomena leaves behind a distinct signature, a calling card written in the language of stellar orbits and galactic structure. Yet when we examine the jellyfish, we find their core stellar disks remain remarkably intact, their spiral arms often pristine and undisturbed. They are like victims of a perfect crime, robbed of their most precious resource, while their fundamental structure, their very skeleton of stars, is left untouched. This paradox forces us to look beyond the visible, beyond the familiar forces of gravity and internal galactic engines. We must consider an influence more subtle, yet more pervasive and relentless. We have to confront the idea that the true culprit is not another galaxy at all, but the seemingly empty space between them. For centuries we conceived of the void between galaxies as just that, a perfect sterile nothingness. But this is perhaps one of the greatest misconceptions in all of cosmology. The vast chasms that separate members of a galactic cluster are not empty. They are filled with a substance so diffuse, so rarefied, it makes the best vacuum we can create on Earth look like a dense fog. This is the intracluster medium, the ICM. It is an immense, invisible ocean of plasma, primarily hydrogen and helium atoms stripped of their electrons, and it is searingly, unimaginably hot. Heated to millions of degrees by the constant gravitational squeezing of the cluster's dark matter halo, and by shockwaves from ancient supernova, this ethereal gas is the ghost in the cosmic machine. It exerts no meaningful gravitational pull of its own, and it is completely transparent to our optical telescopes. Yet within this invisible inferno lies the answer to our mystery. For a galaxy falling into a cluster for the first time is not like one ship passing another in the night. It is like a fragile wooden vessel sailing directly into the heart of a hurricane. The physics at play is surprisingly intuitive, a principle you've felt every time you've held your hand out the window of a moving car. We call it ram pressure. The force you feel isn't from the air hitting your hand, but from your hand slamming into the air. It's a pressure born of motion. Now scale that concept up to the heavens. Imagine a galaxy, a spinning disk of 100 billion stars and trillions of suns worth of cool life-giving gas plunging into a galaxy cluster. It isn't drifting, it is screaming through the intracluster medium at speeds exceeding 1,000 kilometers per second, more than 2 million miles per hour. At this velocity, the tenuous, almost non-existent plasma of the ICM suddenly behaves like a physical barrier. It becomes a relentless, suffocating headwind. This cosmic gale, this ram pressure, does not affect the stars. Stars are tiny, dense points of matter with immense gravitational self-control, like individual bullets in a sandstorm. They punch right through. But the gas, the diffuse interstellar medium that weaves between the stars, is a different story entirely. It is a vast, delicate sail catching the full force of this invisible tempest. The initial impact is a shockwave of stunning proportions. As the galaxy plows into the ICM, the gas at its leading edge is violently compressed, squeezed into a dense, glowing ridge. This bow shock, invisible in optical light, is the first sign of the assault. Behind this front, the cosmic wind howls through the galactic disk. It begins to push, to scour, to peel away the galaxy's atmosphere of gas layer by layer, starting with the most loosely bound material in the outer halo. The force is immense, a continuous and overwhelming pressure that the galaxy's own gravity, its own internal cohesion, struggles to resist. It's a battle of wills, the gravitational anchor of the galaxy, versus the kinetic fury of the cluster environment. And in this battle for the gas on the outskirts, gravity is destined to lose. The gas is lifted, torn free from its stellar home, and flung backwards into the galaxy's wake, forming the very tentacles that give these objects their name. This is ram pressure, stripping a process of slow, inexorable, and utterly transformative violence. It is not a collision, it is an ablation. The galaxy is being systematically flayed alive by the very space it inhabits. To truly grasp the intricate dance of this cosmic theft, we can't just rely on theory, we must see it. But how can we watch a process that unfolds over hundreds of millions of years? The answer lies within the digital heart of our most powerful supercomputers. Here, cosmologists become celestial architects building entire universes from scratch. They begin with the fundamental laws of physics, gravity, hydrodynamics, thermodynamics, and seed a virtual cosmos with dark matter and primordial gas. Then they press play and watch as eons of cosmic time flash by in mere days. They can build a galaxy cluster, a sprawling metropolis of dark matter, filled with its searingly hot ICM. And then they can aim a carefully constructed spiral galaxy, rich in cool gas, directly at its heart. What these simulations reveal is nothing short of breathtaking confirmation. We watch on screen as the virtual galaxy begins its fall. As it crosses the invisible boundary into the cluster, we see the first effects. A pressure front builds up. The gas on the leading edge glows brighter as it's compressed. Then the stripping begins. Wisps of gas, color-coded for density and temperature, begin to peel away from the edges of the disk, like paint being blasted from a wall by a pressure washer. The simulation allows us to see the process in exquisite detail, a perspective forever denied to us by real-time observation. We can see how the galaxy's own rotation complicates the stripping, how the gas is not just pushed back but also twisted into elegant corkscrewing filaments. We witness the formation of instabilities, eddies and whirlpools in the trailing wake, where the stripped gas and the ambient ICM mix in a turbulent froth. Critically, the simulation shows the stars remaining almost completely unperturbed. They sail onward their orbits barely tweaked, utterly oblivious to the fact that the very soul of their galaxy, its potential for future life and creation, is being torn away and left behind. By tweaking the parameters, the galaxy's speed, the density of the ICM, the angle of its approach, we can generate a whole family of jellyfish galaxies. We see galaxies with long, straight tentacles, and others with short, clumpy ones. We see some that have lost only their outer gas, and others that have been stripped almost to their very core. The variety we see in the simulations perfectly mirrors the stunning diversity we find in the real universe. It is this powerful correspondence, this digital echo of reality, that gave astronomers the confidence they were finally on the right track. The computer models weren't just producing beautiful pictures, they were solving the crime. But a simulation, no matter how sophisticated, is only a model. To prove beyond any doubt that ram pressure stripping is the culprit, we need to catch it in the act. We need to gather forensic evidence from the crime scene itself. This requires us to become cosmic detectives, viewing the universe not just in the familiar rainbow of visible light, but across the entire electromagnetic spectrum. Each wavelength of light tells a different part of the story, revealing a different piece of the puzzle. We begin where we always do in the optical. With the penetrating gaze of telescopes like Hubble, we see the stars. We see the resilient shining body of the galaxy, the spiral arms still defiantly tracing their ancient graceful patterns. This is the victim's portrait. But we also see something more. Embedded within the ghostly tentacles, often hundreds of thousands of light years from the parent galaxy, we see brilliant, searingly blue knots of light. These are stellar nurseries, cocoons of newborn stars. Their presence is a profound clue. It tells us that the stripped gas is not dead or inert. It is collapsing under its own gravity, igniting into new suns, even as it is being violently torn from its home. This is star formation happening in the most unlikely of places, not in the calm, protected disk of a galaxy, but in the chaotic, turbulent wake of its own destruction. The optical view gives us the beautiful, tragic anatomy of the jellyfish, but it cannot show us the invisible weapon responsible for its wounds. For that, we must change our vision entirely. We must turn to a form of light so energetic it passes straight through our bodies, a light our eyes could never see X-rays. With space-borne observatories like the Chandra X-ray telescope, we can finally perceive the intracluster medium. The invisible becomes visible. When we point Chandra at a jellyfish galaxy, the universe's grand deception is revealed. The background, which appears black and empty in an optical telescope, is now filled with a faint ethereal glow. This is the multi-million-degree plasma of the ICM, shining in high-energy X-rays, and where this glowing medium meets the oncoming galaxy, we see exactly what the simulations predicted. We see a sharp curved edge in the X-ray emission, a cosmic bow shock where the hot gas is being piled up and compressed by the galaxy's supersonic passage. It is the invisible wake of an invisible boat rendered visible. We can even detect a corresponding shadow or cavity in the X-rays directly behind the galaxy, where its own stripped gas, which is much cooler, has displaced the hot ICM. Seeing this bow shock is the astronomical equivalent of finding fingerprints on a weapon. It is direct, unambiguous proof of a powerful hydrodynamic interaction. We are no longer just inferring the existence of a cosmic headwind. With X-ray vision, we are watching it blow. This is the smoke from a still-smoking gun. But there is one more crucial piece of the puzzle. We've seen the stars and the newborn stellar nurseries in the optical. We've seen the searingly hot plasma of the ICM in X-rays. Now we must trace the victim's own material, the cold, dense gas that is the primary fuel for star formation. This gas is the lifeblood of the galaxy, and it does not shine brightly in either optical or X-ray light. To track it, we need to listen for its faint whisper at the longest wavelengths of light radio waves. Using arrays of giant radio dishes like the Very Large Array or ALMA, we can tune in to the specific frequencies emitted by molecules like carbon monoxide and neutral hydrogen. These molecules are the building blocks of stars, and they exist only in the coldest, densest pockets of the interstellar medium. When we overlay a radio map onto the optical and X-ray images of a jellyfish galaxy, the story comes full circle with stunning clarity. We see vast continuous streamers of this cold gas being pulled directly out of the galactic disk and flowing seamlessly into the trailing tentacles. The radio observations show us precisely where the galactic fuel tank has been ruptured and how the fuel is being siphoned away. We can measure the velocity of this escaping gas and confirm that it is moving away from the galaxy, consistent with being pushed by an external force. We can even quantify the sheer amount of gas being lost, often billions of solar masses enough to build billions of new stars, all being cast out into the void. This multi-wavelength view is the final irrefutable piece of evidence. The optical shows the body, the X-ray reveals the weapon, and the radio traces the bleeding. The case, it would seem, is closed. Ram pressure stripping is the beautifully violent mechanism responsible for creating these magnificent celestial apparitions. Through the combined power of theory, simulation, and observation, we have unmasked the force sculpting these galaxies. It is a testament to our ingenuity, a story of solving a mystery that unfolds on scales of space and time that beggar the imagination. We understand now that a galaxy is not an island entire of itself. Its fate is inextricably linked to the environment it inhabits. For a galaxy entering a cluster, the price of admission is a trial by fire, a stripping away of its future potential. The process is both destructive and in a strange way creative. It is a mechanism of galactic transformation, turning a vibrant gas-rich spiral into a quiescent anemic relic. We have identified the cause, the relentless cosmic wind of ram pressure. We have witnessed its effects across the spectrum, from the shock-heated plasma to the stolen trails of star-forming fuel. But in solving one mystery, we have uncovered another, perhaps even more profound. We now know how the gas is stripped, but this revelation forces us to ask a new urgent question. What happens next? What is the ultimate fate of this stolen gas, this river of lost potential, now flowing through intergalactic space? And what becomes of the newborn stars ignited within these ghostly trailing tentacles, orphaned from their parent galaxy at the moment of their birth? We have found the culprit, but the story of its consequences is only just beginning. And so we watch these spectral tentacles, these bleeding wounds of gas and newborn stars, drift behind their parent galaxy. We see a cosmic creature caught in a current it cannot escape. But the true drama of this encounter, the profound and irreversible consequence, is not what is happening in the trailing filaments of light. It is what is happening back inside the galaxy itself, within the spiral arms that are being systematically, brutally hollowed out. What we are witnessing is not just a spectacle of light and colour. We are watching the slow, methodical murder of a galaxy's future. For a galaxy, life is creation. Its vitality is measured by its ability to gather vast cold reservoirs of hydrogen gas, and through the alchemy of gravity compress them into stellar nurseries. These nurseries are the luminous, vibrant nebulae that paint the spiral arms with brilliant pinks and blues, the crucibles where new suns are born. This process is the galaxy's heartbeat, the engine that drives its evolution, the very source of its light and its potential for life. The gas is everything. It is the fuel, the raw material, the lifeblood. Ram pressure stripping acts as a cosmic tourniquet, cutting off this vital supply. The relentless flow of the intracluster medium is not just plucking at the edges. It is a pervasive hydrodynamical force that permeates the entire galactic disk. Imagine a hurricane not of air but of superheated plasma, a billion-year storm that a galaxy must fly through. At first, it's the most tenuous gas that goes the diffuse warm halo that surrounds the galaxy like an atmosphere. This is the galaxy's first line of defense, and it is stripped away almost instantly, a silent, invisible loss. But the wind does not relent. It presses deeper into the spiral arms themselves, where the slightly denser clouds of atomic hydrogen reside. These are the primary fuel reserves, the gas that will one day cool and collapse to form the next generation of stars. This material is much harder to dislodge, anchored by the galaxy's immense gravity. Yet the pressure is constant. It is a form of cosmic erosion, a sand-blasting effect on a galactic scale. And over millions of years, even these vast reservoirs are scoured away, torn from their gravitational moorings and cast into the void. The galaxy is now hemorrhaging its future. The most dramatic effect, the one that gives these objects their name, is the stripping of the dense molecular clouds themselves. These are the coldest, most tightly bound clumps of gas, the very heart of the stellar nurseries. When the ram pressure becomes strong enough to overcome even their immense density, the effect is catastrophic. The process can trigger a final brilliant burst of star formation within the clouds, as they are compressed by the shock of the wind even as they are being pushed out of the galaxy. This is the tragic beauty of the jellyfish tentacles. They are not merely trails of gas. They are star-forming regions that have been evicted from their home. They are the galaxy's own children, born in exile, destined to wander the intergalactic dark. You're seeing the last defiant gasp of a dying system, a final flurry of creation happening outside the very structure that was meant to nurture it. Back in the disk, the consequences are stark and unforgiving. With its fuel supply draining away, the galaxy's star formation rate begins to plummet. It is a process we call quenching. Quenching isn't an event. It is a slow, creeping death. The brilliant, massive blue stars which burn hot and fast are the first to disappear. With no new gas to form replacements, their short lives end in spectacular supernova explosions, and their light simply winks out. The glowing pink nebulae, the HII regions, ionized by these young energetic stars, fade to black. The spiral arms, once clearly defined by these beacons of new life, begin to lose their structure, their sharp edges blurring as the contrast between bright young stars and the darker dust lanes diminishes. The galaxy's vibrant blue and pink hues are slowly replaced by the monotonous yellow and red light of an older decaying stellar population. The galaxy is aging prematurely, forced into a state of stellar senescence. It is being transformed from a dynamic living spiral into something else entirely. It is becoming a ghost of its former self. Over hundreds of millions or even billions of years this metamorphosis completes. The spiral structure dissolves completely. The disk becomes a smooth, featureless lens of ancient stars, and the galaxy settles into a new classification, a lenticular or S0 galaxy. Sometimes the transformation is so complete it resembles a small elliptical. It has become a passive quiescent object, a cosmic museum piece, containing the relics of its creative past but holding no promise of a creative future. Its journey through the cluster has sterilized it, robbing it of the very essence of its galactic identity. It still contains billions, perhaps trillions of stars. It still has a powerful gravitational field, a supermassive black hole at its core, and a vast halo of dark matter. But the engine has been shut down. It will drift through the cluster for the rest of eternity, as a red dead relic, a silent testament to the brutal power of its environment. This forced evolution is one of the most powerful mechanisms shaping the demographics of the universe. It helps to solve one of the great mysteries of galactic morphology. Why do we see so many vibrant star-forming spiral galaxies in the quiet isolation of the cosmic field, yet so few in the dense crowded cores of galaxy clusters? And why are those clusters so overwhelmingly dominated by red, quiescent lenticular and elliptical galaxies? Ram pressure stripping provides a direct and elegant answer. It is the environmental process that governs the urban development of the cosmos, transforming the newcomers that fall into the galactic metropolis. But to truly appreciate its unique role, we must distinguish this process from the other dangers lurking in these cosmic cities. The universe, after all, has more than one way to dismantle a galaxy. The most famous of these is a far more visceral and violent process, tidal stripping. If ram pressure is a slow, poisoning, tidal stripping is a brutal gravitational assault. It occurs when a smaller galaxy passes too close to a much more massive one. The immense gravitational pull of the larger galaxy exerts a differential force across the smaller one. It tugs more strongly on the near side than the far side. This difference in pull the tidal force is the same phenomenon that creates ocean tides on Earth, but scaled up to an unimaginable degree. The result is not a gentle scouring of gas, but a catastrophic dismemberment. The smaller galaxy is stretched, distorted, and literally torn apart. Stars, gas, dark matter, everything is ripped away in two great arcing tails that trail from opposite sides of the victim, a clear signature of gravitational disruption. Tidal stripping is a gravitational guillotine. It is brute force. It affects all components of the galaxy, not just its gas. Entire star clusters, vast streams of stellar material, can be pulled out, forming immense ghost-like bridges between the interacting galaxies. This process is responsible for some of the most spectacular and distorted shapes we see in the cosmos galaxies, locked in a gravitational tug-of-war, their structures twisted into knots and loops. While it can certainly remove gas and quench star formation, its methods are entirely different from ram pressure. It is a messy, indiscriminate demolition. Ram pressure, by contrast, is a hydrodynamical scalpel. It is a force that interacts primarily with the gas, the interstellar medium, while leaving the stars and the dark matter halo almost completely untouched. Stars are so dense and so compact that the wind of the intracluster medium flows around them as if they weren't there. The dark matter interacting only through gravity is entirely immune. Ram pressure therefore performs a very specific kind of surgery. It hollows a galaxy out from the inside, removing its fuel, while leaving its fundamental stellar structure, its bones, largely intact. This is why a jellyfish galaxy looks the way it does. We see the gas being stripped in one direction, the direction opposite to the galaxy's motion through the cluster, while the stellar disk remains a coherent rotating system. Tidal stripping, on the other hand, produces two opposing tails and dramatically disrupts the stellar disk itself. By comparing these signatures, astronomers can act as cosmic detectives, reconstructing the crime scene to determine the culprit. Was this galaxy choked to death by the hot wind of the cluster, or was it torn limb from limb by the gravity of a monstrous neighbour? The evidence is written in the geometry of the stripped material and the integrity of the remaining stars. Of course, the universe is rarely so simple. These processes are not mutually exclusive. A galaxy falling into a cluster might first experience gentle tidal forces from the cluster's overall gravitational potential, a process sometimes called harassment, which can loosen the gas in its outer disk. This pre-processing makes the galaxy even more vulnerable to the effects of ram pressure when it finally plunges into the dense core. The two mechanisms can work in concert, a 1-2 punch that accelerates the galaxy's transformation and ensures its rapid demise as a star-forming entity. This intricate dance of forces explains the rich tapestry of galaxy populations we observe. Clusters are not just collections of galaxies, they are ecosystems where the environment dictates survival and evolution. The morphology-density relation, the observation that elliptical and lenticular galaxies dominate dense environments while spirals thrive in isolation, is a direct consequence of these transformative processes. Spirals are the natural state of a galaxy left to its own devices, slowly accreting gas from the cosmic web and spinning it into stars. But when that galaxy is drawn into the gravitational well of a cluster, it enters a new and hostile domain. It is subjected to forces it never experienced in the quiet cosmic field. Ram pressure stripping, more than any other single process, is the agent of this change. It is the primary reason why the cores of galaxy clusters are galactic retirement homes filled with ancient red stellar populations. It is the mechanism that ensures that the history of a cluster is written in the shapes and colours of the galaxies it contains. Each red quiescent galaxy in the heart of the Coma or Virgo cluster is a survivor, a veteran of a violent infall, a system that was stripped of its creative potential billions of years ago. The profound consequence, then, is not just the transformation of a single galaxy, but the shaping of the entire cosmic landscape. This process dictates the distribution of star formation across the universe, concentrating it in the less dense regions of the cosmic web, and suppressing it in the great galactic conurbations. It is a form of cosmic regulation, a feedback mechanism that prevents clusters from becoming unimaginably bright with runaway starbirth. The gas that is stripped from hundreds or even thousands of galaxies enriches the intracluster medium itself, seeding it with heavier elements forged in the hearts of stars. This enriched gas then cools over billions of years, sometimes flowing back towards the central dominant galaxy, in the cluster, providing a trickle of fuel for its own modest star formation in a grand cycle of galactic life and death. The jellyfish galaxy, therefore, is not an anomaly. It is a snapshot of a fundamental ongoing process. It is the visible evidence of the invisible hand that sculpts the universe, a fleeting moment where we can see the raw physics of environment in action. We are watching the architecture of the cosmos being built one stripped galaxy at a time. The bloodletting we witness is not just the end of one galaxy's story of creation, it is a vital chapter in the much grander story of the universe's evolution. But a tantalizing question remains. We have focused on the galaxy left behind the hollowed-out shell destined for quiescence. What about the stolen material? What becomes of that vast luminous tail of gas and newborn stars now adrift in the sterile darkness between galaxies? Does that stolen lifeblood simply dissipate and fade away? Or could it, against all odds, begin a new and unexpected story of its own? And so, the paradox deepens. For so long we have seen these magnificent wounded structures as cosmic victims caught in a tempest not of their own, making their lifeblood splayed across the void. We pictured a passive surrender, a galaxy simply overwhelmed by the sheer brute force of its environment. But this is where the story pivots, where victimhood gives way to a breathtaking, violent, and utterly creative act of defiance. The jellyfish galaxy is not merely being torn apart, it is actively participating in its own spectacular transformation. This isn't a death scene. It is a metamorphosis written in fire and gas, played out on a scale that defies our terrestrial imagination. To truly understand this cosmic ballet, we must move beyond the simple idea of a galactic wind and look at the intricate dialogue between the aggressor and the galaxy itself. It is a conversation of physics, a struggle between two colossal forces. On one side, you have the relentless invisible hurricane of the intracluster medium, the ram pressure we have come to understand as a celestial sandblaster. On the other, you have the galaxy's own formidable defense, the immense gravitational anchor of its dark matter, halo, and the collective pull of its billions of stars. This is not a simple erosion. It is a dynamic, complex assault where the galaxy's own internal structure, its density, its rotation, its magnetic soul determines the shape of its own unravelling. Imagine a ship not just being battered by waves, but actively using its keel and rudder to navigate the storm even as its sails are shredded. The jellyfish galaxy, in a similar way, is an agent in its own destiny. The process begins at the outermost fringes where the galaxy's grip is weakest. Here, the tenuous, diffuse halo of warm gas, the galaxy's atmospheric veil, offers little resistance. It's the first to go stripped away almost instantly in a silent, invisible shearing that leaves the underlying structure exposed. This is the first layer of the onion peeled back, revealing the denser, more tightly bound spiral arms. Now the ram pressure encounters a far more stubborn obstacle. This is not just thin gas. This is a complex ecosystem of dust lanes, giant molecular clouds and stellar nurseries all swirling in a gravitational dance, choreographed by the galactic core. The force of the intracluster medium travelling at millions of kilometers per hour slams into this rotating disk. It is a moment of cosmic impact. The leading edge of the galaxy is compressed, squeezed like a sponge, and this compression is the secret, the critical turning point in our story. This is where the VLT, the Very Large Telescope perched high in the Chilean desert, becomes our celestial eye. Using its revolutionary MUSE instrument, astronomers can perform what amounts to a spectral autopsy on the galaxy in real time. MUSE doesn't just take a picture, it creates a three-dimensional data cube capturing a spectrum of light for every single pixel in the image. This allows us to map not just the location of the gas, but its velocity, its temperature, and its chemical composition. We can literally see the shockwave propagating across the galactic face. We witness the gas on the leading edge being crushed, its density skyrocketing, its temperature flaring. It is a galactic shield buckling under an immense and continuous pressure, and in that buckling a new potential is forged. Simultaneously, the pressure begins to shear material from the disk. It can't dislodge the stars which are gravitationally locked in place, but the gas between the stars is a different matter. It flows, it bends, it tears. Think of it like a river flowing past a submerged rocky outcrop. The water is deflected, forming turbulent eddies, and wakes behind the obstruction. In the same way, the intracluster medium flows around the dense star-filled heart of the galaxy, and in its wake it pulls the less gravitationally bound gas with it. This is the beginning of the tentacles. This is the moment the galaxy starts to bleed. The gas that is torn away is not uniform. The looser, warmer gas is stripped first, forming the long ethereal filaments that give the jellyfish its name. These can stretch for hundreds of thousands of light-years, ghostly trails, marking the galaxy's tortured path through the cluster. But what about the densest, coldest gas? The vast molecular clouds, the very cradles of star formation. These are the crown jewels of the galaxy reservoirs of fuel for future generations of stars. They are far more resilient. Held together by their own powerful gravity, they act as cohesive clumps within the broader galactic disk. The ram pressure struggles to dissolve them outright. Instead, it peels them away from the galaxy like stubborn barnacles being scraped from a hull. They are dislodged, but they are not destroyed, and this is the profound revelation. The galaxy bleeds, but its blood is not sterile, it is fertile. These massive clouds of cold, dense gas, once torn from the gravitational safety of the galactic disk, are now adrift in the galaxy's wake. They are orphaned, but they are not inert. Here, our other great eye on the cosmos, ALMA, the Atacama Large Millimeter, Sub-Millimeter Array, takes over the narrative. While the VLT sees the hot glowing gas and the brilliant young star's ALMA is sensitive to the faint cold emissions from molecular hydrogen, the raw material for starbirth. Its 66 interconnected dishes work in unison to pierce the cosmic veil, showing us what is hidden from optical telescopes. And what ALMA has revealed within the tentacles of jellyfish galaxies is nothing short of astonishing. It has found immense reservoirs of cold molecular gas, the very same material found in the star-forming nurseries of our own Milky Way streaming for tens of thousands of light years behind the parent galaxy. These are not just wisps of gas, they are coherent, massive structures, the seeds of creation cast out into the desolate intergalactic space. The same crushing force that stripped these clouds from their home now becomes their midwife. As these clouds tumble through the turbulent wake, the pressure from the surrounding hot medium squeezes them. It is a relentless, suffocating compression from all sides. Densities inside these orphaned clouds rise to a critical threshold. Gravity, which was always present, suddenly finds it has the upper hand. Pockets within the larger cloud begin to collapse under their own weight, fragmenting into smaller, denser cores. Temperatures at the heart of these cores skyrocket, climbing to millions of degrees. The threshold is crossed, nuclear fusion ignites, a star is born. This is not a gentle or isolated process, it is a firestorm. The compression triggers a wave of star formation so intense, so furious, that it lights up the tentacles like a string of celestial lanterns. The VLT's Muse instrument confirms this spectacular sight, revealing chains of brilliant, massive cobalt blue stars tracing the path of the stripped gas. These are O-type and B-type stars, stellar behemoths dozens of times more massive than our Sun, burning with a ferocious intensity. They are ephemeral, living fast and dying young, but for their brief million-year lives they illuminate the darkness of the intergalactic void. They are a testament to creation in the most unlikely of places. We are watching for the first time star formation happening outside the confines of a galaxy. These are stars born in exile. This makes the jellyfish galaxy a laboratory unlike any other in the universe. It provides a unique ready-made experiment for understanding one of the most fundamental processes in cosmology, how stars form. On Earth we can create theoretical models and run computer simulations, but we can never replicate the extreme conditions found in a galaxy cluster. Here, nature has set up the experiment for us. We can study how star formation is triggered by external pressure rather than the internal dynamics that govern starbirth in quiescent galaxies like our own. We can measure the efficiency of this process, asking how much of the stripped gas is successfully converted into new suns. The answers have profound implications. They help us understand why galaxies and clusters eventually stop forming stars altogether, transitioning from vibrant blue spirals into aging red and dead elliptical galaxies. The jellyfish represents that transition in action. It is the missing link, a snapshot of a galaxy being transformed from one type to another, its fuel for future generations being violently stripped away, but not before one last spectacular burst of creation. The implications ripple even further outwards. The intricate dance between the galactic gas, its internal magnetic fields, which act like cosmic elastic bands resisting the stripping, and the turbulent intracluster medium, is a perfect testing ground for our theories of plasma physics and magnetohydrodynamics. The delicate thread-like structures seen in the tentacles hint at the presence of powerful magnetic fields that are being stretched and amplified, channeling the flow of gas like microscopic wires. By studying these filaments, we can probe the invisible magnetic architecture of galaxy clusters, a critical but poorly understood component of the cosmic web. The jellyfish in its agony reveals the unseen forces that shape the universe on the larger scales. We see more than just gas and stars. We see entire star clusters, gravitationally bound families of hundreds or thousands of stars forming within the tentacles. These are in essence newborn globular clusters, but formed under the most bizarre circumstances imaginable. They are born on the run, destined to wander the vast empty spaces between galaxies for eternity. Will they remain as cohesive units? Will they eventually disperse their constituent stars, travelling alone through the void? Or could they, over billions of years, be captured by the gravity of another galaxy, becoming integrated into a new cosmic family? These are the questions that now drive the research. The jellyfish galaxy has opened a new frontier, forcing us to reconsider the boundaries of where life, or at least the potential for it, can begin. A star born in the lonely darkness of the intergalactic medium is no different from a star born in the heart of a grand spiral. It will forge heavy elements in its core. If it hosts planets, those planets will receive its light and warmth. The act of stripping is not just an ending for the parent galaxy. It is a beginning, a seeding of the void with the potential for new worlds. We are forced to reevaluate our entire perspective. The term bleeding now seems so inadequate, so incomplete. It implies only loss, only injury. What we are witnessing is far more nuanced. It is a galactic exodus, a violent expulsion of star-forming potential into a new barren territory. The galaxy is not just losing its gas, it is actively enriching the intergalactic medium with heavy elements forged in the hearts of these new short-lived stars. When these massive blue stars in the tentacles finally die, they will explode as supernovae scattering carbon, oxygen and iron into the surrounding hot gas of the cluster. It is a form of cosmic recycling on an epic scale, a process that ensures the material for future star and planet formation is not forever locked away inside galaxies, but is distributed throughout the cosmic ecosystem. The jellyfish is a cosmic benefactor, enriching its environment even as it is being consumed by it. Our climax then is not one of simple destruction, but of violent generative complexity. The jellyfish galaxy is caught in a cosmic crucible, a place of immense pressure and transformation, where the lines between creation and destruction are blurred into a single seamless process. It is a story of resistance, where the galaxy's own gravity and structure fight back, shaping the very nature of the assault. It is a story of unexpected birth, where the force of that assault becomes the trigger for a final brilliant burst of star formation in the most desolate of locations. And it is a story of legacy, where the galaxy seeds its environment with the elements of life, ensuring that its sacrifice contributes to the ongoing evolution of the universe. We came looking for a victim for a simple answer to why these galaxies were bleeding gas into space. Instead, we have found a dynamic and powerful engine of cosmic change, a key player in the grand interconnected story of how galaxies live, how they die, and how even in their apparent demise they pave the way for new beginnings. The blood of the jellyfish we now see is the seed of new stars, new clusters, and perhaps somewhere in that vast and lonely darkness, new worlds. And what becomes of the galaxy that is left behind, the hollowed-out shell that survives this ordeal, its story, its final transformation into a ghostly relic of its former self, is the final haunting chapter in this cosmic epic. And so we return to where our journey began. We find ourselves once more before that ghostly impossible image, a magnificent spiral galaxy, a pinwheel of 100 billion suns bleeding its very essence into the void. When we first looked upon this celestial phantom, we were confronted with a profound and unsettling mystery. It was a spectacle of cosmic violence that defied our neat categories, a vision of a galaxy being unmade before our very eyes. We asked a simple, haunting question: why? Why was this city of stars hemorrhaging its future, casting its precious star-forming gas into the lonely darkness between its neighbours? The answer, as we have discovered, is as elegant as it is brutal. It is an answer written not in a single event, but in a process, not in a solitary action, but in an environmental crucible that forges the fates of countless galaxies across the universe. We have journeyed deep into the heart of galactic metropolises, into the chaotic, searingly hot realm of galaxy clusters. There, amidst the gravitational whirlpool of thousands of galaxies, we found the culprit, a relentless invisible hurricane. An ethereal medium of superheated plasma, the intracluster medium, pervades these cosmic cities, a substance 1,000,000 times less dense than the best vacuum we can create on Earth, yet vast enough to exert an unimaginable force upon anything that dares to enter it. We learned that when a gas-rich galaxy like our own Milky Way is captured by the cluster's immense gravity, it begins an orbital dance of death, plunging through this plasma at millions of kilometers per hour. This is no gentle passage. It is a headwind of unimaginable power, a a cosmic gale that slams into the galaxy's own reservoir of cool hydrogen gas. This is RAM pressure stripping. It is the force that acts as a cosmic sandblaster scouring away the delicate life-giving material held loosely in the galaxy's outer disk. We saw how this force doesn't just remove the gas, it sculpts it, pulling it back into the long trailing tendrils that gave these apparitions their name jellyfish galaxies. Our investigation did not stop with simply identifying the mechanism. The true revelation, the twist in our cosmic story, was that this act of destruction was also an act of creation. Within those spectacular bleeding tentacles, we found a paradox. The very pressure that was tearing the gas from its home was simultaneously compressing it, shocking it into gravitational collapse. We witnessed the impossible stellar nurseries ignited in the empty space behind the galaxy, far from the safety of its spiral arms. Strings of brilliant blue newborn stars illuminated the stripped trails, a final defiant burst of life from a galaxy being slowly starved. These are the orphans of the void suns, born into exile, destined to wander the intergalactic darkness alone. We saw how these jellyfish are not a final state, but a fleeting snapshot, a transitional phase in the grand narrative of cosmic evolution. They are a bridge. They show us in exquisite and tragic detail precisely how a vibrant star-forming spiral galaxy is transformed into a quiescent red and dead, elliptical or lenticular system. They are the missing link, the Rosetta Stone, for understanding why the most massive and ancient galaxies in our universe are almost universally barren of new stars. They are the living proof that a galaxy's destiny is not solely its own to control. It is profoundly shaped by the neighborhood, the cosmic city in which it chooses to reside. This is a lesson in cosmic ecology, demonstrating that no galaxy is an island entire of itself. We even ventured into the shadows, exploring the unseen forces at play. We considered the role of the galaxy's own magnetic field, that invisible shield that attempts to anchor the gas against the storm, and how its intricate structure can be twisted and dragged out, creating magnetized filaments that channel the flow of material. We peered into the heart of the storm, the turbulent wakes and swirling vortices that trail behind these cosmic swimmers, and realized that this process is far more complex, far more beautifully chaotic than a simple headwind. It is a fluid, dynamic ballet on a galactic scale, a performance of such complexity that our supercomputers strain to simulate it, revealing the delicate interplay between gravity pressure and magnetism. Our journey has taken us from a curious anomaly to a cornerstone of astrophysical understanding. The jellyfish galaxy is no longer just a cosmic spectacle. It has become an essential laboratory, a controlled experiment conducted by nature itself over billions of years. By studying them, we are not merely observing a peculiar fate. We are gaining a visceral, immediate insight into the physics that governs the growth and death of all galaxies, including perhaps one day our own. The Milky Way is currently in a cosmic backwater, but we are on a collision course with our neighbour Andromeda, and together we will one day merge and perhaps fall into the Virgo cluster. The fate of the jellyfish could be a preview of our own distant future, a glimpse into a time when our galactic home will face its own trial by the intracluster fire. Yet for every question we have answered, for every layer of the mystery we have peeled back, we have uncovered a dozen more, each more profound and tantalizing than the last. Our comprehensive picture, it turns out, is still just a sketch, and the edges of the canvas fade into tantalizing darkness. We have charted the beginning of the river of gas as it leaves the galaxy, but we are now faced with the immense question, where does that river truly end? What is the ultimate fate of this stripped material? This colossal offering of a galaxy's soul to the cluster, does it simply disperse, becoming an indistinguishable infinitesimal addition to the hot intracluster medium? Does it evaporate under the searing heat, its cool essence lost forever in the billion-degree plasma, its potential for new stars extinguished? This seems the most likely answer, a quiet and final dissolution. But the universe is rarely so simple. Our latest observations hint at a far more intricate destiny. Could some of this stripped gas, shielded in dense cold knots, survive its journey through the inferno? Could these clouds of molecular gas, now untethered from their parent galaxy, continue to collapse under their own gravity? Imagine for a moment the possibility of orphan star formation on a grand scale, not just individual stars, but Entire clusters, even small dwarf galaxies, congealing out of the wreckage left in a jellyfish galaxy's wake. These would be objects of an entirely new class intergalactic star systems born from recycled material, true children of the cluster itself rather than any single galaxy. Detecting such faint isolated systems is a monumental challenge, like finding a handful of glowing embers scattered across a dark continent. It requires a new generation of telescopes with unprecedented sensitivity instruments designed to hunt for the faintest whispers of light in the blackest corners of the cosmos. The search is on a cosmic treasure hunt for the lost tribes of stars born from the diaspora of a dying galaxy. This leads us to an even grander, more fundamental question about the very life cycle of the universe, the concept of gas recycling. Is a galaxy cluster, a closed system, a cosmic terrarium where nothing is ever truly lost, only transformed? The gas strip from a jellyfish galaxy feeds the intracluster medium, but what happens next? For decades we have theorized that in the very centers of the most massive clusters, where the pressure and density are highest, this hot gas can eventually cool down. It could rain back down onto the colossal central galaxy, the cluster queen, in what we call a cooling flow, providing it with fresh fuel to power its own star formation or feed its supermassive black hole. If this is true, then the jellyfish galaxy is not just a victim, it is an unwitting participant in a majestic cluster-wide ecosystem. It is part of a cosmic food web. The smaller galaxies are the prey their gas consumed by the environment, which in turn nourishes the giant predator at the center. The bleeding of one galaxy becomes the lifeblood of another. This would be a stunning confirmation of the interconnectedness of cosmic structures, revealing a flow of matter and energy that binds the fates of thousands of galaxies together. But proving it is incredibly difficult. Tracing a specific parcel of gas from a jellyfish tentacle all the way to the core of a central galaxy hundreds of thousands of light-years away is currently beyond our technological reach. It remains one of the most compelling and sought-after goals in extragalactic astronomy. And what of the invisible forces we're only now beginning to map? We spoke of magnetic fields as anchors, but their role may be far more active, far more dramatic. How do the vast cluster-wide magnetic fields interact with the personal magnetic field of an incoming galaxy? Does this interaction create a kind of magnetic friction, helping to pull the gas away even more effectively? Or conversely, could magnetic draping, where the cluster's field lines wrap around the galaxy, like a cloak, actually shield some of the gas, protecting it from the full force of the ram pressure wind? These fields, though ghost-like and intangible, could be the hidden architects shaping the fine details of the jellyfish tentacles. They might be responsible for the strangely coherent filamentary structures we see within them, preventing the gas from immediately dissipating and helping to channel it into the star-forming knots. Mapping these fields is a Herculean task. They don't shine in visible light. We can only infer their presence and structure through the faint polarized radio waves emitted by cosmic ray electrons spiraling along the field lines. New radio telescopes sprawling across entire continents are just beginning to give us the first blurry maps of this magnetic web, revealing a universe threaded with invisible forces that guide and shape the flow of cosmic matter in ways we are still struggling to comprehend. Then there is the crucial question of time. We see these jellyfish galaxies in a single moment of their existence. But how long does this spectacular violent transformation actually take? Is it a brief catastrophic event that unfolds over a few tens of millions of years, a blink of an eye in cosmic terms, or is it a slow grinding process of attrition that can last for 1 billion years or more as the galaxy makes several passes through the dense cluster core? The answer likely depends on the size of the galaxy, the density of the cluster, and the exact trajectory of its orbit. To build a true timeline, we need more than just snapshots. We need a cosmic photo album. We must hunt for galaxies at every stage of this process, the pre-jellyfish, that are just entering the cluster, their gas disks beginning to warp and ruffle at the edges, the peak jellyfish in the full throes of stripping with their magnificent tentacles stretching for hundreds of thousands of light years, and most importantly the post-jellyfish, the exhausted survivors, their tentacles faded, their gas reservoirs depleted, now set on a final inexorable path to becoming red and dead. By finding and studying large populations of these objects, we can piece together the entire chronology of this transformation, turning a single frame into a complete motion picture of galactic evolution. And we must ask, is this extreme process confined only to the most violent environments in the universe? Galaxy clusters are the cosmic equivalent of Manhattan at rush hour. But what happens in the suburbs? In the quieter, less crowded galaxy groups where only a handful of galaxies orbit one another, ram pressure stripping should still occur there, but it would be a much gentler breeze, not a hurricane. This subtler form of gas removal, often called starvation or strangulation, might not create the spectacular tentacles of a classic jellyfish. Instead, it could slowly and quietly remove the tenuous halo of hot gas that surrounds a galaxy, cutting off its supply of future fuel. The galaxy wouldn't be stripped bare in one go, it would simply be unable to replenish the gas it uses up in star formation, leading to a slow, gentle decline into quiescence. Detecting this gentle cosmic asphyxiation is one of the next great challenges, pushing our instruments to their absolute limits to see the faintest, most diffuse gas at the edges of distant galaxies. So where does this leave us? We stand at a remarkable vantage point in the history of science. The jellyfish galaxy, once a mere curiosity catalogued by automated surveys, has blossomed into a rich and profoundly informative field of study. It has become a nexus, a point where the physics of plasma star formation, gravity and magnetism all converge in a single breathtaking spectacle. It teaches us that the universe is not a static collection of objects, but a dynamic evolving ecosystem driven by powerful environmental forces. It shows us that even the most massive and majestic structures are not immutable, but are subject to change, to transformation, and ultimately to a form of death. But it is the nature of this death that provides the final, most awe-inspiring lesson. What we have witnessed is not an ending in the conventional sense. It is not an annihilation. It is a metamorphosis. The galaxy as it once was ceases to be. Its vibrant, spiraling youth gives way to a serene, quiescent old age. This is a violent, brutal transformation, a cosmic trial by fire. Yet from this apparent death, new life emerges. The galaxy bleeds, and from its wounds, new suns are born. The gas, the very soul of the galaxy, is not destroyed. It is bequeathed to the cluster, recycled into the cosmic environment, potentially to fuel future generations of stars in other galaxies, in other corners of the metropolis, billions of years from now. The jellyfish galaxy is a testament to one of the deepest truths of the cosmos, that creation and destruction are not opposites, but are two faces of the same fundamental process of change. It is a story of loss and legacy, of sacrifice and renewal written in fire and gas across the vastness of intergalactic space. And as we continue to gaze into the deep, armed with new questions and ever more powerful tools, these beautiful bleeding phantoms will continue to guide us, revealing the intricate and violent beauty of how our universe constantly, relentlessly remakes itself. The mystery is not solved, it has simply become grander,